So now we want to look at the fourth problem in the homework, which is number 21. And we want to compare the ratings of TV and internet services from a number of different providers. And so what we're really looking at here is we want to tell if there's a difference in the mean service rating between the TV and internet services. So here you notice that the same company, we're doing two different measurements on them in a sense. So we're really looking at the difference of two means, the difference between means of two related populations. We'll put it that way. So I'm going to go ahead, I'm going to compute the differences first for each of the companies. Okay. So this is essentially the data that I'm going to be working with here. And now I'm going to compute some summary statistics. So I need to do any sort of thing, whether it's hypothesis, test, or confidence interval. I need the average of the differences. Okay. I need the standard deviation of the differences. And finally, I need the sample size, and I'm told that there's 14 different companies, so I have 14 of the differences. Okay. The last thing I'm going to compute is I'm going to compute the standard deviation of d bar, the estimated standard deviation. Okay, so this is going to be standard deviation of d bar, which is going to be the standard deviation of d over the square root of n. This is just like x. Really, these d's are just like x's now, right? So this is equal to this divided by the square root of this, and we get the following. And I'm going to round these off a little bit just to make them look nice. Okay, so now we're ready to do some damage. All right, so now we want to do a hypothesis test. So at a significance level of 0.05, is there a difference in the mean service rating between the two internet services? So we're going to start off. We're going to state the hypotheses. Okay, so my null hypothesis is that mu d is equal to 0. Let me put it like this. Yeah, okay. So the average of the differences is equal to 0. Okay, that's the same as saying that go up here. That the difference in the mean service rating, okay, is not different. And the alternative is that if we computed all these differences and we took the mean, it's not 0. Alright, so now we need our test statistic. This is the easier part of this problem, really. Usually this is the hard part. But here we know that it's just going to be equal to, it's going to be a t-score, but it's going to be equal to this, and this is 0, so it's this minus 0, divided by the standard deviation of d bar. Okay. That's a very large value, even for a t-distribution. We know the p-value should be very, very small. So we want to go ahead and we want to compute the p-value. Now I'm doing a two-tailed test with a negative test statistic, so I'm just going to say twice t dot dist. I'm putting the 2 here because I'm doing a two-tailed test, and I'm not putting a 1 minus because t is less than 0. So I'm looking at the percentile or the lower tail. So we got this. My degrees of freedom are going to be n minus 1. So it's this minus 1. I'm looking at the cumulative. And there's my p-value. It's extremely small, right? So the decision rule is actually quite easy to use. So in this case, and I'm going to stretch this over because this will get a little long here. P is equal to 0.123456709, which is definitely less than 0.05, which is equal to alpha. So therefore, this is 7 times 10 to the minus 6, right? If I bring this over 1. Whoops, actually I want this to be 1 less, right? Yep. I bring this over 1, 2, 3, 4, 5, 6. It really doesn't matter, it's less than 0.05 in either case, but we'll do it correctly. And now I'm finally ready for the conclusion. So we're going to say at a significance, let me put the thing here. So we're going to reject the null hypothesis. Okay. And now we're ready for conclusion. So we would say at a significance level, of 0.05, we conclude that the mean ratings of TV we'll say for the TV and internet services are not equal. Okay. And that's pretty much it for the hypothesis test. What assumption is necessary about the population distribution in order to perform this test? Actually, we don't know. We really need to know very much about the population distribution, but the differences have to be roughly normal. Okay, they have to be at least be symmetric. If these two are symmetric, it helps. But we're really interested in this. This has to be somewhat symmetric. Okay, it doesn't have to really be normal, but it should at least be somewhat statistics, somewhat symmetric. Okay. If these two populations are not skewed, usually this won't be. Okie doke. We can use a graphical method to assess the validity, and basically here, we would want to check and see that this looked like it came from a normal distribution. So we could go ahead and we could make, say, like a histogram. Okay, for part C. I'll just do this over here. So we start off computing some basic statistics, right? We need the max. Here. We need the min. Okay. And we could just make, we can see that the range is going to be 6, and so therefore we can make the bin size 1. Okay, so now we can go ahead and we can make our bins 1, 2, 3, 4, 5, 6, 7. We'll just be careful about it. Okay, now we're ready to go ahead and make the histogram. It's going to be a little hard to see because we don't have a lot of data values, and the bins are very coarse, but we'll see what we get. Okay, so our input range is right here. Okay, our bin range is here. And actually, I have to be careful. I need to do this over. Actually, I need to go the other way. I need to go up to -7, -6. be slick and do this really quick, and then pull this down. I need to go this way. Okay, let's do it again. Okay, so the input range will be the same, but it didn't. It erased it when I canceled. Okay, then the bin range is here. Okay, whoops. Me and technology today, I'll tell you, we're just not getting along. Okay, there we go. Okay, bin range is there. And the output range I'll put here. I'll tell you. Okay. One more time. There we go. The output range is really there. And we'll put it right there. And now we're ready. Okay. So now we can make a histogram out of this, okay? And so I'll just highlight these guys. Insert, scatter plot. And we'll change chart type. Okay. It's not looking particularly symmetric. Okay. So there could be problems. It's a little hard to tell because we don't have a lot of data. And so we don't have a lot of statistics for each cell. Okay, so, and the reason why is, we see a fluctuation here, but we also kind of see a fluctuation here. So one of these is a fluctuation, and we can't tell which it is. If it's this one, or this one. All right. So if it's this one, then it probably, the density would end up here. So it's kind of hard to say. Here's the thing. We can't really say it's symmetric necessarily, but it's also very hard to say it's skewed because it's not skewed here because this is not skewed here because we don't have a tail. So I would say it's not too far off from being symmetric. It's a little bit off. Okay, now we want to do the confidence interval. So graphical methods, when you have on the order of around 12 points, they're not going to be very good. Generally, that rule of 30 actually holds for a lot of reasons, and one of the reasons why is it also holds for histograms. It's hard to get good histograms when you have below 30 data values all the time. Okay, let's go ahead and do the last part, part D. We want to do the confidence interval. So we need the critical value. And if we go back and look at this, it's going to be the 95th% confidence interval. So I'm going to use t.inv. And I'm going to 0.025. I have 13 degrees of freedom and -1. Okay. And my margin of error is just equal to the critical value times standard deviation of d bar, which is, I know, I'm going to have to get out of this command because I can't move what I want. So let's just get out of this command. Be careful when you're in Excel and you're in a command because you can do things that will cause the whole program to screw up and you have to force shut it down. Okay. Now I'm going to make this margin of error, not meow. Okay. So this is equal to absolute value of this times standard deviation of d bar. Okay. And now we're ready. It's just d bar plus or minus that. So the lower endpoint is just equal to d bar minus this. And the upper is just plus. Now you're going to notice that 0 will not be in here. And we know it can't be. Because we know, since we rejected the null hypothesis, that D, the number that's on the right-hand side of the hypothesis statements, cannot be in here. So there's our 95% confidence interval. Okay.